So I would like to welcome everybody and from the whole world, and we are very happy to meet you online. And today, this is our fourth webinar for this series, and our topic is about the machine learning. And this webinar organizers are Professor Ye Yongxuan and Professor Pan Yanchen, and also myself. And I'm the new arrival, will start my job next week in the National Central University. So today we are very, very happy to have Dr. Ye, and we can also call him Gordon. And then he will present us about his research and especially how to apply the machine learning to study the exoplanets. And Dr. Ye, he finished his PhD in 2021 at UCL, and now he is a postdoc fellow also in the UCL. It's in UK. So the talk will have 45 minutes long, and afterwards we will open the audience to ask the questions to Dr. Ye. So I think now we just welcome Dr. Ye to start his talk. Please, Gordon.
Yeah, thank you. Thank you everyone for joining. Thank you for the very kind invitation from Taiwan Space Union. I'm very happy to be here today to share with you about some of the latest news from exoplanets and with machine learning as well. So, so we are basically 20 years after, I think, no, 20 to 30 years after we discovered the first exoplanets. And a lot has happened since then. So I'm just going to give you an overview about what I'm going to talk about today. So if you ever get lost, just remember that our central question of today's seminar is about how do we develop the technologies for rapid and robust planet characterization. That will be our main aim. So I'll start off with a very high level overview about the introduction about exoplanet characterization. What are the problems? What do we do to characterize these exoplanets? The second, we'll go with, okay, how do we use machine learnings to characterize our atmosphere? And I'll also talk to you about what are the caveats, why won't this sort of, why is it not sort of working right now? What do we need to do? That leads on to the aerial data challenge. And if we are ambitious enough, then we'll go to the fourth objective, which is basically interpreting black box models with explainable AI technique. So let's get started. So this is my team at UCL. We have actually quite a diverse team. You can sort of divide that into two different branches. One branch is the sort of traditional techniques theory approach, which is led by Professor Giovanna Tiniti, who is also the PI of the aerial space mission, which I'll talk about later, and her previous students. And then the other branch is led by Professor Ingo Wortmann. We are looking at basically machine learning techniques applied to various problems in exoplanets, especially exoplanet atmospheres. But you can also see that there are also different components in the team, such as we have our center manager, we have our comms officer, which are crucial to our team as well. So let's look at the solar system right now. So we are in our own galaxy, Milky Way, and the red circle indicates the location of our solar system. Up until now, we've got 5,400 confirmed planets in 4,000 different systems. But most of them, if not all, they're actually discovered within our own Milky Way. And simply because if we want to discover planets from other galaxies, it's simply very far away and very hard. We start off with discovering planets such as hot Jupiters. Basically, they are Jupiter-sized planet, but they are very, very close to the star, to their host star. So a typical example is that they will have a 3-day period. So basically, every 3 days they can celebrate a new year. But then people thought, oh, are they actually the most common type? then later realize when we have more data from Kepler, more data from TESS, we realize that no, they're actually not. And the most common planets, they're actually Earth size, or what we call a super Earth size. When we say super Earth, we actually means that they are slightly bigger than Earth, but smaller than Neptune. That raises another question. Is habitability common or not? But then there are also many other questions that has to be. So sometimes we define some sort of a green belt based on the distance of the planet to the star. So for example, our Earth is actually within that, but that's actually not the single criteria, because if you think about Venus, they're actually within the habitable zone. But Venus obviously is not habitable. And later, so we will have Gaia mission, which is basically an ESA mission. They expect to yield 10K more planets, but we expect that there will be many more planets to be discovered. So really is a big data problem. And here's a diagram showing you all of the different missions that ESA and NASA put together, especially for exoplanets as well. So on the first row, you've got the dedicated exoplanet mission, and on the second row, basically top bottom panel, you've got the exoplanet sensitive mission, basically missions that are not dedicated for such exoplanet, but they can detect exoplanet. These missions, they represent detection missions. So basically, their main job is to detect exoplanet, look at them, find them out, and that's it, no more. You can see that it's concentrated in between 2003 to 2018. That's the main focus. But then slowly and slowly, they are moving towards characterization. So once we find them, which is great, we know their mass, we know their radius, but we need to know their atmosphere. And that's where characterization comes in. And then my talk will lean towards Ariel, which is a mission due to launch in 2029. So going down, why do we emphasize so much on exoplanet atmosphere? So first of all, it tells us about history, the formation history of the planet. It tells about whether it's got impact or not by comet, because that will actually be revealed in the atmosphere. Clouds, obviously, we can tell that from our atmospheres. Star radiation, how intense is the radiation, and that really determines whether you can actually have life or not. And it also determines some of the chemical process that we have, such as the ozone layer in the Earth, ion escape from the atmosphere, volcanic activity, such as what you can see in Venus, that will actually reveal itself in the atmosphere. So we really, and then obviously biosignature, life, which is what we say one of the holy grail of exoplanet atmosphere, is that can we actually detect such thing. But spoiler, we haven't been able to do that yet, but that's basically what studying the exoplanet atmosphere can tell us about what lies within the planet itself. So what do we do to do that? So among all the other techniques that we use to discover exoplanets, many of them actually focus on what we call the exoplanet transit. So if you imagine that the circle, the orange circle that we have at the middle, that's the whole star, and then the smaller red circle there is actually our planet. And as it orbits around the whole star, at some moment in time, it will basically come between the plane of the stellar disk, and that will blocking some of the starlight. And from there, we can actually detect the presence or of the planet. But if you observe that in different wavelengths, you can actually use this technique to detect the presence of molecules and various other effects happening in the atmosphere. So if it is transiting in front of the star, what we get is what we call the transmission spectrum. And then if it goes around and behind the star, which we call it secondary eclipse, we don't see that here, but that's actually what we have is a day sign emission from the planet. So we're characterizing the design of the planet. To give you a more concrete example on that, uh, what you're looking at right now is a schematic of, you have your star on your left, and then you have the planet, and then you're moving towards, and then the light are filtering across the planet towards the Earth. And this kind of spectrum that are formed by this filtration, we call it the transmission spectrum. And it's really useful for detecting the presence of molecule and characterizing the terminator uh, of the atmosphere. And then if it goes back to the back of the sun, we can characterize the design of the planet, which is really helpful and really sensitive to the temperature, pressure, structure of the planet. And with the reflection spectrum, basically you are looking at the light bouncing off the exoplanet clouds. You can see what the particles, do they have any small particles inside the atmosphere? How small are they? What are the particles? What do they make of? And that really tells us a lot about the atmosphere. And if you look at the scale of it, so the starlight is 1 to 100,000 photons. We are looking at basically for every 100,000 photons, where there may be one photon that actually filtered through the atmosphere. So the challenge is really there, and it's really hard to characterize. And for now, what we can really tell is, do they have water? Do they have methane, etc., because the challenge is really hard, and we haven't reached a state where we can do reflection spectrum yet. And on your right, you've got different missions here. So we've got Hubble Space Telescope, which is still operating, and then you've got the newly launched JWST spectrum, which is will characterize 50 to 100 planets in very high detail. But both of them, you can see that they will only together to only characterize about 200 exoplanets. But come in sort of 5 years time, when we have Ariel, you basically start characterizing exoplanet in a bigger scale. We have 1,000 planets in low details, and then from these 1,000 planets, we'll characterize 500 planets in high details, and then we will select 50 planets for very high details observations. So, but we are the launch of JWST really pushed us into a new era of complexity here. So on your left, you've got a spectrum coming out from Hubble and Spitzer as well, combining together. And what the spectrum really tells us is that the different band that you have in different wavelengths tells you about the presence of a molecule. So here we have H2O, sodium, and potassium. And then on your right, the black dot there, the black error bar that we have, they're actually coming from Hubble. But then if you see the color dot, that's actually coming from James Webb, the new telescope that we have on the sky. And you can just see how much detail there are for one observation. And but then if you inspect it more closely, you can see that the best fit line, which is basically the black curve, is actually not very aligned with the colored dot. And we don't know what happened yet. We suspect that it's actually some kind of instrument systematic, but we don't know what that is. That could be some other atmospheric phenomenon that we haven't characterized yet. The problem is with James Webb is that the quality of data is so much higher that we might not have account for all of the physical phenomena that is happening within the planet. So that actually comes to one of the main scientific challenges in exoplanets, is that how do we model this kind of extreme climate? We have one climate model, one climate example on the Earth that we can really characterize. But how do we extrapolate? Because Earth is about 25 degrees Celsius or 4 degrees Celsius in some cases, but they are not 2000 Kelvin, 3000 Kelvin. Those are extreme cases. And how do we characterize that? Secondly, how do we predict their behavior, their chemical behavior when they are at hundreds or thousands of degrees? How do we understand their planet formation and understand what do we mean by biomarkers. Is it just water? Is it ozone? What do we mean by that? So those are the main scientific challenges. So to give you a visualization of what we mean by these challenges, this is a simulation from Cho et al. 2021, where he actually built a GCM, global circulation model, which is a 3D representation of a planet, and we actually use similar forms of it in predicting our weather. But then he applied it to exoplanets, so 2000, 3000 Kelvins, very, very hot. And you can see so just how many details there are. And we are only modeling the dynamics of these planets, not the radiative transfer, not the chemistry. And it takes a week for them to have this kind of visualization. And if you're doing simulations yourself, you know that there's just one simulation. There are many other simulations that you need to try before you can get to that result. Chemistry, right now we only model them in 1D, and we haven't considered their various different reaction rate. And if we consider their reaction rate, again, they will be very slow because you have to wait for them to settle into a equilibrium state. And for that, you have to evolve them step by step. And that, again, takes about 6 hours to 8 hours to complete one simulation. And that is already something that we can't handle in exoplanets. So why can't we handle that? Because all of these advanced adventures, they are in the theory side of things. So, but then we have to match these theories to our observations so that we can check whether our theory actually makes sense or not. But for now, we can't do that. And that actually lies in one of the key, that problem, that bottleneck is actually lies with the tool that we use to interpret this observation. So what we use is what we call the atmospheric retrieval. We use this technique to infer atmospheric properties from our observations, and it involves a search of a potentially large parameter space to search for the best parameter that could have given rise to this observation. And on your right, you've got a visualization of how the whole thing works. So basically, you have your observation, you have your prior, basically your belief about, okay, where this parameter lies in. You put in this retrieval algorithm where you have your forward model, your atmospheric model, and then you also have your spectrum, and then you compute the likelihood, basically how close your theoretical spectrum is to your observation. And then you do that for 10,000 times, 100,000 times to try very basically different, you search for different combination of this spectrum. And then in the end, you have your best fit model and also the posterior distribution, basically the probability, this conditional probability distribution of your observation of how these parameters might have distributed. So these are all good for one planet, for one simple planet. But then if you want to go for higher dimensional retrievals, if you want to go for more extensive, you can't do that anymore. Basically, once we reach about 30 dimensions. So this is diagram showing you the complexity or the cost of running this kind of algorithm. So y-axis is the cost, x-axis is the dimensionality or the number of parameters that you have. And you can see that it is increasing exponentially. Right now, we are about, typically we use 30 to 40 parameters. But then if you go for JWST or more, then you are going for to need 50 or even 100. So we need machine learning to help us with the job. And in recent years, the number of machine learning literature has increased exponentially. So the orange graph is cosmology, exoplanets. It really starts in sort of 2017. And people are trying to explore different ways to apply machine learning in exoplanets to help speed things up. So what are the problems that we're facing right now? The central problem is, given an observation, what is the possible distribution of key atmospheric parameters such as temperature, what are the abundances of water, abundance of methane, and in research, we actually look at them in distribution. So here is just a simple diagram showing you what we're looking for, what are the distribution of temperature, the methane, radius, etc., and the correlations. And if you find it familiar, and you are probably right, because what we're dealing with is what we call the inverse problem. So you start off with some physical parameters, which will give you a full spectrum, but we won't see that. Instead, we see a corrupted form of it, which we call it the observed spectrum. And then we use adversarial retrieval to sort of come back to help us to find the physical parameters that could have given rise to this kind of full spectrum. And that is actually a flavor of the inverse problem. How likely is X tilde caused by Y? So just a very brief intro on adversarial retrieval. This is for serial distribution that we have, and we need to solve a Bayesian formulation in order to get to that. But it's difficult because it's easy to compute the likelihood and the prior, which is the upper terms in denominator, but the denominator is the evidence, and the evidence is difficult to compute and it's intractable when you have a lot of parameters. But then on the other hand, the evidence is actually very useful to compare different models, because in atmospheric characterization, you have many different assumptions about the atmosphere. And what we need to do is to find the best assumption that can explain our observations. So what people do, they have the observation, they have the forward model, they put it into a likelihood function, basically just measuring the distance between your observations and my theoretical models, and then you sample. You basically search through a huge parameter space. You use MCMC or use nested sampling, use some smart searching algorithm until you find the perfect combination. And then people also come up with new network approach, is that, well, instead of using this kind of sampling approach, you generate a lot of forward models, basically a lot of atmospheric models. You train a new network, which is NN here, and then to produce a distribution. And then in test phase, once you train a new network, you'll be able to apply your new network on the observation, and then out you go, distribution. It's very quick. And a lot of people have actually tried that as well. We've tried random forests, convolution models, generative models, and then you can see the trend. So we go from simple model first, such as random forest, MLPs, which is basically one of the foundations of machine learning models, and then we go for more elaborate models such as generative models, Bayesian networks, simulation-based inference, etc. and etc. So I'm going to show you one of the latest that we have from. So what you're looking at here is that from Martinez et al. 2022, they actually applied a CNN, and then they compare it with a result from the traditional approach, from the sampling approach, multinest. So the red one is from CNN, and the blue one is actually from multinest. The aim here is to have the best match, to a perfect match between the two. And obviously it's not the perfect match, but you can already start to see the new network is able to learn the correlation, basically all the different boxes that you have, apart from diagonal ones, they are looking at the correlation between different parameters. And the new network is able to pick up this. But what it wasn't able to pick up is the shape of it. You can see the multi for the blue line, they are actually have some non-linear shape, but then for the CNN, it was sort of stuck in a Gaussian like shape. And the other thing is that in order to account for the observation uncertainty, they have to train the entire neural network in a single observation uncertainty. But then we know that if we have deal with observations, that every single observation has different uncertainty. So to summarize this kind of popular approaches, with sampling, you have flexible input ranges. You can basically put in any wavelength range that you like, 0 to 1, 0 to 10. But for neural network, you can't. Once you train it, that's it. That's your input. You have 55 data points in your input, 55 features maybe. That's 55 features. You can't change that anymore. Same as the output. Once you predict a new network for temperature and water, that's it. That's 2 targets. You can't do it for 4 targets or 5 targets unless you retrain the whole thing. Uncertainty quantification A implicit neural network nowadays at least is that every data point is absolutely don't have error bar. So um, and it's difficult to put in observation uncertainty into a new network unless you do some ad hoc approach like scattering them or augmenting it in some other ways. But otherwise, there is no formal inclusion. But on the other hand, with sampling, you actually include uncertainty into the equations, into the likelihood function. So that's a formal inclusion of that. They are not new network, they're not Bayesian framework, or even if they're Bayesian, then they're using Gaussian as a prior, as opposed to any other prior that you might want. They can't perform model selection, but then they have a very good advantage. They can apply it to 1,000 or 10,000 spectra in a fraction of a second. But for sampling, you can't. Every single spectrum takes you about 2 hours to a day. And if 1,000, you multiply that by 1,000. So that's a long time. And our question is, can we get the best of both worlds? Can we basically look at all of these pros and cons and come up with a way, a middle ground between that? And that's the way we came up with, is that we use what we call our VI approach, or variation inference approach. So that's the schematic on the right, comparing with the conventional approach on the left. And you can see that we swap over different things. So let's say that our forward model on the left, we swap it by what we call a diff tau. So basically a differentiable forward model, something that would give us the gradient. But apart from that, it's completely the same as our forward model. And then instead of optimizing it through a likelihood function, we optimize the evidence lower bound. I'll talk about that later. And then we convert the entire problem from a sampling problem. Basically, you're searching blindly through a parameter space, you turn it into optimization problem, and then in the end, you have the same output to posterior distributions. So just to quickly tell you about what the evidence lower bound is, instead of dealing with, so on the top right corner, you've got Bayesian equations. So we know that because of the evidence terms, the denominator, the whole thing is intractable. So basically, you can't compute a analytical formula. You have to resort to some sort of approximation. Instead of sampling these intractable posterior to get an approximation from, what we seek to find is a surrogate distribution Q that can best approximate our posterior distribution, basically what we showed on the diagram on the right, where the gray contour there, the distribution, is our ground truth distribution. And the purple one, Q, is our surrogate one. And the problem is you want to find the best surrogate distribution that can match your underlying posterior distribution. And if you want to do that, the objective function is known as the evidence lower bound. And given the name evidence lower bound, it actually estimate the lower bound of your evidence. And I'll tell you about what sort of advantage that we have with that. So just to give you a diagram showing you what exactly happens is that given that, let's say that the gray one is our distribution Q, that our surrogate distribution that we want to optimize, and then P theta given D, that is our posterior distribution in red that we want our Q to match that. And to do that, you can basically optimize Q through gradient descent, and then you go to that, you optimize, and then you extract the optimal parameters that govern your distribution Q. If it's a Gaussian, then let's say that this is mean and standard deviation. Perfect. If your posterior distribution, underlying distribution, is a Gaussian, perfect. You find the problem, you speed things up, great. But the problem is, as with a lot of things, is that most of the things that we encounter in nature, they are non-Gaussian at all. You can't see that. But you don't know whether they're Gaussian, but most of them are not. And how do you do that? How do you find a perfect distribution and that enables you to do that? Most of the time, it is impossible because you don't know the underlying form. And here comes the normalizing flow, which is a machine learning algorithm. And its main job is you'll be able to transform from one distribution to another distribution, an arbitrary distribution. So on your right, you have an animation that tells you about exactly what happened. So here is what is happening right now is that you go from initial 2D Gaussian distribution, and you go through a normalizing flow, which basically you can think of it as massaging the distribution into a half moon distribution. And combining both of them together, the evidence band and normalizing flow together, you'll be able to match the posterior distribution very, very well. So this is one of the examples, one of the results that we have. So we simulate a spectrum in Hubble resolution, and then we assume that they have some water and some clouds in the atmosphere, and then we want to retrieve 6 targets, parameters from the atmosphere. And then this is from the sampling approach. All good, you have the correlations. And then this is what we have when we apply our variation inference approach, which gives us a very nice agreement between the two. But we didn't stop at that. We then switch a gear into aerial resolution. The main difference between the Hubble and aerial is that aerial is much more extensive. So Hubble gets you from, if you look at the lower left, you can see that it goes from 1.1 to 1.6. But for aerial, it goes from 0.5 to 8 micron. So it's a very extensive, very long wavelength range. And then we are able to simulate it and get a very nice observations, very nice agreement between the sampling approach and the variational inference approach. And with that, we can actually use 75% less forward models, because for every computation of abstract model, it takes time, it takes resources, and then we are able to reduce that by 75%. And also, we are able to do, using the evidence bound objective function, we are able to do model selections based on the value that we've got from them, and then we are able to say which model is the best. So on the table on the lower right, we actually have a small table showing you about we try different models, and then we can see that our complete model has the best result overall. So this is just to show you about the good agreement between them. This is just to show you how our variation inference approach, how they actually do in action. So we start off with a uniform distribution. We don't assume anything about the atmosphere apart from that they are uniform distributed between certain minimum and maximum valued. These are parameters on the diagonal that we're trying to optimize to the temperature of the atmosphere, the radius of the atmosphere, and the different gases that we have. So I'm going to start this animation here. And then the red square is the correlation that we want to focus on. And then you can see that in the beginning, the radius of the planet is very strongly constrained. And then slowly and slowly, the network is able to figure out that actually there are correlation between these different parameters. And remember that they start off from a uniform distribution, and then they can form correlation by themselves. They can learn the correlation by themselves. And one of the good things is that they are not overly constrained. You can see from CO that it remains a very broad distribution, because you actually can't characterize CO from aerial, and it correctly reflect that. So I'm just gonna do a summary of that. Is that with sampling approach, we are able to do a lot of things, but then we can't scale them up. For neural network, on the other hand, it's very rigid. Once it's trained, it's done. You can't do anything about it unless you retrain the whole thing, but then you can apply to a lot of different planets. With our approach, we are able to merge sort of the good things from neural network, borrow some of the good things from neural network, and apply it to our traditional sampling approach. And we sort of get the best out of both worlds by reducing the number of forward models that we need in order to get to our result. But the problem is we are still doing it planet by planet, so one planet to another planet. And it's nowhere near the speed of a neural network where you can basically apply them in a fraction of seconds. So what are the caveats? You don't get free lunch out of a framework. You don't just apply machine learning without any sort of caveats, drawbacks. So the first major drawback is that it requires a differentiable model. But if you want your model to be differential, automatic differentiable, you have to apply in specific frameworks such as TensorFlow, PyTorch, or JAX. And that requires you to rewrite your entire algorithm into this, because usually people do it in Fortran or Python. Now you have to rewrite the whole thing. We have not explored multi-model distribution. Basically, if you have distribution with two peaks, will that work? We don't know. As I mentioned before, the inference time with our VI approach, they remain incomparable to neural networks, where you can do basically apply to a lot of planets in a fraction of seconds. It's also subject to the same bias as we have with adversarial retrieval. It's just to show that while it's approach, it is not the magic pill. As with any optimization task, it can get trapped in the local minimum really, really easily. So the conclusion for the first part is that we develop a framework to perform adversarial retrieval using optimization as opposed to using sampling. Um, we're able to reduce the forward model computation, and it only requires one observation to train. So you don't actually need to produce a large library of data as opposed to all the other machine learning algorithms. It only requires one observation. It is flexible because we can change from from Hubble to Aerial without needing to generate a lot of data sets. But more work is to be done to make sure that this is stable and robust. Now, with all this caveat that we have in our mind, we're like, what are the other approach? There might be other approaches that are better than using normalizing flow, using some fancy machine learning algorithm. There may be better approach that we may have overlooked because we are just one researcher or one team of researchers using applying machine learning. So we came up with this idea of aerial data challenge, is that we want to invite everyone to join this problem, to tackle a problem, not just ourselves. So the main goal of the aerial data, I'm not going to go through all of these goals here, but essentially you can imagine a scenario where you have to explain yourself to a colleague about the problem that you're dealing with, but they don't necessarily have knowledge about the thing that you're working on. So what you need to do then is you need to package your problem in a language that they will understand, such as you have to, if I'm describing myself to a machine learning engineer, I'll need to use terms such as feature, loss functions, target in order for them to understand. And the whole thing about the aerial data challenge is that we package a problem in astronomy, any problem, and right now it's related to aerial, and we package them in a way that machine learning engineers can understand, so that they can work on it using the materials that we provide to come up with a solution in a game-like situation. So we actually got sponsors by various bodies in the UK and Europe as well, such as DIRAC, UK Space Agency, CLINES, the French Space Agency, and obviously European Research Council and Aerial as well. We've also got a network of international partners as well across the UK, Europe, and Japan as well, and also industry partners as well. If you're interested in joining us, we're more than welcome, because we have our 2024 competition coming out, and we're actively looking for partners. Here, I want to also present my my appreciation on the NCU. They actually help us to promote this challenge as well this year. So what is Aerial? I've been talking about Aerial. So Aerial is ESA M4 mission, and then they orbit around the L2 orbit, and then they are going to observe 1,000 exoplanets. And we have a list of countries that help us with that. Is a big consortium. And we have, the problem is, we go from how do we handle aerial data and how do we use this challenge to best support aerial's activity. So we start off in 2019, and then we've had various achievements. Due to the shortest of time, I'm going to skip through them really quickly. But essentially, we got to a Portuguese television about this aerial data challenge, which is pretty nice. And then we reached over 250 participants in our 2022 competition. We got into NeoNIFS, one of the most prestigious machine learning conference, and we've got over 50% of them are coming from our international audience, and also with the rest coming from all around the world. I think this year in 2023, we've also got a couple of participants coming from Taiwan as well. Um, so we also checked our competition among others, and then we realized that we are actually quite popular in terms of for every pound we spent, we compared that with all the other new NIFS competition, and then we got the third place, meaning that people are actually quite interested in our competition or in general astronomy competitions. So the problem that we're dealing with again is about atmospheric characterization. Basically, given an observation from aerial, can you predict the 6 key atmospheric properties of the exoplanet? And that is for 2022 and 2023 edition. But for 2024, for next year, we won't be doing that anymore. So we want to go to different directions. And the setup for a machine learning data challenge is that you've got a data set, and then the participants work on the training data, and then they test themselves on the test data. But the implicit assumption is that they're coming from the same distribution, which in aerial case is not. Instead, you have one set of training data assumption for your training data, and then for your test data, you should be testing it with different atmospheric assumption, because no matter how good your simulation is for aerial, when you look at a real planet, they will not be anything like your simulation. So we want to test that example. And for that, we actually build a giant database. It's one of the largest public database, and it's been field tested by AI machine learning practitioners all over the world, at least by 250 of them. And we also compare that with other public data set that we have. So the main idea of this table here is not to show that, oh, we are, we're the most correct. What we're trying to say here is that we try to be comprehensive, we try to be less wrong. And this is the latest version that we have, and is also publicly available. It accounts for various different events such as star, the planet, and the mass radius relationship of the planet. So that's the setup. And our main question is, if you train a neural network using a training distribution with one specific atmospheric assumption, can they retain the same performance when you apply it to different test set? Would they be biased, and how would it impact? How that might be impact? So what we essentially investigating is what we call a data drift effect, and that is the performance of our top 10 entrants, and that is actually lined up with their performance. So you can see that so the gators on the right hand side, that they have the highest score, and they actually are the first place winner in 2022 edition, and that is their performance when the training data is the same as the test data. All good. But then when the training data is different from the test data, you can see that there's a systematic decline in the performance of these new network models, all of them across the board. There's no exception there. And we can actually see in more details about what is happening. On the left is when you have your training data equals to test data. And we are plotting the prediction against the ground truth, meaning that everything lies on the diagonal. If you have a perfect predictor, everything should lies on the diagonal dotted line. And it is in that case. But on your right, you have the training data when it's not equal to the test data. And you can see that they don't look like, so they are deviating from the diagonal line. And the problem with that is, in the actual case, we don't have the diagonal line to guide us. We don't know when it's working and when it's not working, and that's the problem.
5 minutes. Sorry.
Okay, cool. I will speed things up. Thank you very much. For the 2023 edition, we actually change things up a little bit. We actually say, okay, because we only have given them one training example in 2022, we give them extra example with different atmospheric assumption. Will that actually help? Because usually in machine learning, if you have more diverse data set, it might help. Again, this is the blue line when it's same as training. Again, we're seeing the same phenomenon, that when you have different atmospheric assumptions, they don't work at all. So what does it mean, really? Is that many machine learning solutions, they don't work well when data drift exists. And the reason why I can say that and claim that is we are having a number of different architecture in machine learning architectures, trying the same problem with the same data with the same metric. So we can say that not a lot of machine learning can do that. Um, we cannot really simply apply our trained model to real data and hope that it works on simulation, it will work on real data. It just doesn't work like that for machine learning models. It's not a algorithm that we know exactly what happens. Data drift will happen as soon as there's a change in the planet's atmosphere. And what we need to do is to find a way that can tell us when and why these models no longer works. And here I showed you about the diversity of the solutions here. And you can see there are normalizing flow, there are transformers, mixed density model that are typically applied to generative models. But then at the same time, all the rest are also applied. And that's the advantage of a competition, is that you can get to explore different architecture in 2 or 4 months' time. So I'm going to skip over that. This is a brief overview of our ADC winners, and they come from industry, they come from the University of Florida, and our latest winner, they come from the Harvard University Astro AI team. So I'm going to skip through the solutions, but what it means really for all of them is that they all rely on, the secret is that they rely on existing physical knowledge, and then they implement a lot of it during the pre-processing stage. It highlights that pre-processing your data sometimes outweigh the benefit of having a powerful model, such as using a transformer. Because our winner in 2022, they actually use a feed-forward network, but they heavily pre-process it with their physics knowledge. But then it's a double-edged knife, because remember that the premises of using a new network is that we don't need to have that kind of pre-processing anymore. We can basically use the data to guide the new network. If we use a lot of assumption, our physical assumptions, then chances are we might be missing out some of the physics. And it seems that from our result that it does not mitigate the issue with dataset shift. So as soon as the underlying assumption changes, these pre-processing doesn't really help. So conclusion for the part 2 is that ADC is really a good way to engage with the global AI community, and is open to everyone, no matter you're a student, postdoc, or a professor. Please, you're welcome to join us. It's a cost-effective way of conducting research, because in 2 to 4 months' time, you are able to explore different solutions. Data should be set ahead, and it must be studied, and also that your model and process them really matters and really helps you to score a high score. And at last, I want to conclude that organizing this challenge, it requires really a lot of effort, and it's just a shout out to my team for basically organizing them together and putting up this competition. And I think I've basically almost reached the 45 minutes limit, so I basically stop here, and I welcome any questions that you may have. Thank you very much.
Thank you so much, Gordon. Very wonderful talk, and thank you for you and group paid so much effort on creating this ADC tool for all of us. So now we take questions from audience. If you have questions, you can raise your hands using, if you can see there is a button, can click. So far, no, but I will get the audience some time to think of questions. So may I ask Gordon about, so the Ariel would be the next mission, right?
Yes.
And how do you think about current James Webb Space Telescope? What would be the new challenges? Because now we have JWST, and would it be the providing some challenge for the next mission or not?
Yeah. So JWST is really a very nice. I think as a mission is really great, in the sense that you've got Ariel launching in 2029, but you've got James Webb now, and then the good thing about it is that both of them, they're actually in the L2 orbit. So things that will happen to James Webb, we say that is a very good testing ground for Ariel. And one of the main challenges for James Webb is that you've got a really nice instrument that can basically detect light from very faint source. But the problem is, how do you train this instrument systematics? And the problem is we've never flown an instrument there and observed exoplanet in the L2. And how do you deal with that? And it's actually, I think it's been 1 year since we have the first result from James Webb, but people are still figuring out all of this instrument systematics. And typically, if we know from Hubble, it takes a long time
Mm.
to study these kind of systematics. So
Mm.
that's the challenge.
Wow. Thank you. Any questions from the audience? Or you can just speak if you don't see the right hand button. Today everybody is quiet.
That's all right. I went through quite a few slides quite quickly. So I think it also,
Yes. Ah, here is one. Yeah, please. May I ask how to pronounce your name?
Hi, Professor Cheng. So my name is Surojit Saha from NTHU Taiwan.
Yeah.
So thank you, Gordon, for the wonderful discussion that you had on the machine learning and It's a Planet. I was pretty interested to know how long does your training time takes at the moment, and the hardware that you're using for the training, because I assume there's a lot of data that is being put into your training. If you could just highlight some of those.
yeah, absolutely. So I guess so there are two parts to so because the first part is about training using variational inference. And for that part, I don't actually need to use a lot of fancy hardware GPUs. Actually, I use my laptop to train that um, country to or the popular belief. Because what happens is our data actually is big. You get 10,000 or 100,000 data points, but then for each of them, you've only got 52 spectroscopic points, and that really puts it into a smaller scale, and you don't actually need uh, that big of a machine to train that. And it typically takes about 3 hours to train that. And if you're talking about the aerial data transfer data set that we put on for the participants, you can most of them they are training using their own laptops, or some of them they're using the GPU resource to speed things up, but usually it's not necessary. And the typical time again is about 2-3 hours, simply because of the size of the data set. It takes about 3 GB in your hard drive space. So it's not a big data set.
Yeah, thank you for the question. That what I actually assume too, that the data will not be much bigger in size. So the other point is that under these circumstances, when the data is not large, sometimes we know that some of the machine learning models can like end up in some biases or something like that. So did you come across such things when you have such low amount of data?
Yeah, well, no, I guess the no amount data that we have is that in terms of we don't actually we can because we're doing simulations, right? So you can actually produce how many um samples that you want, examples that you want. For our case, we've got 100,000 of them. That's a lot of them. But when I say low, as in the dimensionality, the number of features that we have is low, but not for the size of the data. But then even with that, you also see biases, even with you have that many data points, simply because what we're dealing with is a problem of you are jumping through. So let's say that you train your neural network for one atmospheric assumptions, and then you jumping through you test it on a different assumption, and then that you introduce a bias immediately because they are two different atmospheric assumptions, and then you're trying to ask a new network to generalize to a different distribution. I hope that answers your
Yeah, I
question.
would definitely agree to you on that. Yeah, thank you very much for the answer.
Thank you. So, or does anyone leave the messages in the chat? I don't see questions. I only see thank you.
No?
Yeah, okay. So, Gordon, what do you think the biggest challenge now for the machine learning? What is the limit actually for this machine learning technique to understand the atmosphere of exoplanets?
Yeah, that's actually a very good question. The biggest challenge I think is how do you go from, because we've done a lot of work on simulations. We've got a pile of there's a slide where I show, there are different authors doing different things, applying different neural networks. So I think what we're lacking is not about our knowledge on machine learning, but the challenge is how do you go from simulation to real data? How do you actually apply that to real data? And I think we are lacking on that, because and part of the challenge, part of the resistance is that yes, we've got these kind of literatures in the field, but no one is applying it in real life. No one is using that to analyze data from James Webb, data from Hubble. They're always using their conventional approach. And I think that's because of the trust issue, that neural net is inherently a black box. And there's a resistance in people to understand and to use them. And I think is also our job is to basically how do we make sure that it's robust. Yeah, that's one of the main challenge.
So when you simulate your, for example, now we have observations have shown this beautiful spectrum. And when you simulate, you mainly how wide the wavelengths you can coverage from your simulation. Can you apply your single simulation to all the wavelengths of the observed spectrum, or you specific simulate certain wavelengths of spectrum?
Yeah, I think when you simulate a spectrum, first of all, when you simulate it, is what we call a full spectrum. So you go from, I don't know, 0.5 to 50 micron. That's the maximum based on the quantum effect that we calculate. But then you can bin it down to any, because we know that that's a full resolutions and no instrument can actually achieve that kind of resolution. And then when you bin it down, you can bin it down to, let's say, James Webb, Ariel, Hubble, anything that you like.
That's very powerful, actually.
Well, it's not my work. It's the work from other people. I just basically, borrow their simulator.
So will you or your group will have some workshop for the ADC, or what is your for a plan to introduce this to the scientists?
Yeah, so we have our Ariel consortium meeting, which happens every 2 years, twice a year, where we introduce the Ariel Data Challenge. And then we've also attached ourselves to machine learning conference. Then that's where we introduce our scientific work, our scientific question to the entire audience. On top of that, we've also planning to have, because we've got a few winners now, a few presenters, potential presentation, we might do a workshop as well, just to tell people about what we've done, but that's the kind of question that we're looking at, etc., etc.
Yes, because I think if audience they are interested, they can further contact you to get those information.
Yeah. Always welcome. If you guys have any questions, you can always ask me offline.
Yeah, so I don't see any hands on so far. And I think now we also approaching 1 hour. So I think we want to thank you again, Gordon, for your wonderful talk. And if the audience have any question, you are welcome. You either send me email, we can forward to Gordon. Is that okay?
Yeah, that's completely fine. That's completely fine. Yeah.
Yeah. And thank you so much. And thank you everyone for your join. And thank you Taiwan Space Union for organizing such a webinar. And thank you so much, Gordon.
Thank you. Thank you for the invitation.
I hope you have a nice day in UK.
You too.
Thank you so much.
As in Taiwan. See you. Bye-bye.